people out again. All right. So, looking here with our acids and bases. First, we're going to start with was what is an acid and a base, and there are different definitions for this. Okay. So the first one is the most common one, and that is the Arrhenius definition. Okay. And so the way Arrhenius had, or if you say Arrhenius, it's fine. I know what you mean. So the way that definition goes is kind of what I had started with to get you to recognize the differences between an acid and base, right? So in our old notes, we said, all right, an acid is something that starts with a hydrogen, all right? And that's where his definition kind of goes, or that's what it goes with, right? And bases will always have that hydroxide thing on them. That's the Arrhenius definition of an acid and base. So what we're going to add to that is that it ionizes to form H+. What ionizes means is that it splits, right? So it kind of like the dissolving idea. So ionizes means it splits into different ions, one of them being an H+, right? So H's are at the beginning of the formula. All right, a base will ionize to form hydroxide. Okay, ionize to form hydroxide. So that's the easy definition, okay? Because it kind of goes with how we're already recognizing it from the formulas, okay? Make sense? So those are the things that we'll notice with those. All right. I think that's all I want to say about that one for now. So what this takes care of for sure is all of your strong acids and bases that we kind of talked about. Okay, because those for sure had an H and then something, or it had a metal and an OH, right? But it didn't take care of our most common weak base, okay? So the most common weak base, if you flip over the page from last week, flip it over, what was the one that has a star next to it? If you flip over your page from last week, NH3, and number 5, right? NH3 is a weak base. This is one that I told you, you're just going to have to memorize this one because it doesn't look like a base, right? There is no OH. That doesn't go with Arrhenius's definition. So this right here is why Bronsted-Lowry, or one of the reasons why he redefined it, okay? So his definition just got a little more detailed, okay? Not just skimming the surface, hey, this is what it looks like, these are the ions it forms. It's more about what those acids and bases are doing, okay? So a Bronsted-Lowry acid is defined as a hydrogen or proton donor. Do we know what a donor is, by the way? So it's a donator, right? So the one who donates, okay? So he's the one who gives the hydrogen, and the base is going to be the H. So it's still back to the proton idea, right? Remember I told you we call those H pluses a proton. So H plus or proton acceptor, meaning he accepts it, all right? And so once again, this is why NH3 is going to be able to now work out, and it's labeled as a base. Okay, so we're going to take this one step further because I want you to at least see this, okay? So up here, I want you to write NH3 and then put a big X over it, because what you're telling yourself when you go back to look at these notes later is that NH3 wasn't covered under the Arrhenius definition of a base. But for Bronsted-Lowry, takes that into consideration, okay? So we've got NH3, we put it into some water, and what it's going to ionize now into is we're going to have this idea of a proton donor and a proton acceptor. So a hydrogen is going to get transferred, okay? So we could form NH4 with a little plus OH with a minus. That right there, what is OH minus telling you? Hopefully you're saying base in your head. Okay, base, yeah, exactly. So base, right? Just like up here. This is where the OH is now going to kind of show up, okay? But do I need you guys to be able to do that? Not necessarily. I need you to know the fact that a Bronsted-Lowry acid is the donor and the base is the acceptor. And then looking at this little equation, who was my donator? Who was the donor out of NH3 versus H2O? H2O, exactly, right? So that was your acid. So go ahead and label it as an acid. And NH3 was the base, which is what we kind of learned. And so what we see is that the acid gave an H plus to the base. And that's where the Bronsted-Lowry definition works. Now, the crazy part about this is that this one shows water as an acid, and you're like, but it's neutral or something. That's what the guy said in the video, right? Yeah, it is. It's actually amphoteric, meaning it can act as an acid, or I could turn around and put acetic acid into water, and it'll act as the base, and it'll form this H3O+, right, the hydronium that we kind of talked about briefly on Thursday. And so water is amphoteric, which just means that it can act as an acid or a base because it's a little bit of both. All right? Okay. I'll kind of get back to that in just a tiny bit. So now what we're going to go over, those are the definitions. Okay? So you got two definitions of what an acid and a base is. All right. Now we're going to talk about the properties. I'm going to kind of go back and forth between these two. But first I want to start with what two things do they have in common, for sure. All right? So the guy in the video that we watched right before this said that they were both considered corrosive. Both considered corrosive. So you can write that first. Okay? Acids and bases are both corrosive, which is a very common misconception. A lot of people, like he was saying, think acids only because you think of battery corrosion. Like if you've ever left a AA battery in like a remote too long and you go to open it, it's all crusty and nasty, right? Corrosion, you hear the word corrosion, you're like, okay, all right, so it's acid, right? But bases do the same kind of thing. So it's not just acids. They're both considered corrosive. They are also both electrolytes. And just a reminder, electrolytes means that it conducts electricity when it's in aqueous form, right? Because it splits into ions. So both acids and bases are electrolytes. So using those two deciding factors, you can't, or not deciding factor, sorry, but if I were to use like conductivity to tell me if something's an acid or a base, you're not going to have any luck with that, right? Because they're both electrolytes. To say, oh, this one corroded something, so that means it's an acid, no, because the other one does too, right? So there's other things that you got to pay attention to. So now the rest of our list is where the differences are going to come in, okay? So first, we have that acids are going to taste sour. Now, are you allowed to eat any of my chemicals? No, okay? But a couple examples of ones that you have tasted before is something like citric acid, which is found in oranges and citrus fruit, any of your sour candies. Vinegar is also another common one. Okay, so citric acid, vinegar, those taste sour. Okay. Bases, on the other hand, taste bitter. A common one is unsweetened chocolate. So, like people who like to bake things, okay? The baker's chocolate. Kale, if you've ever had kale salad. And then the last one is always made us giggle, which is soap. Next thing is going to be about litmus paper, all right? So here I'm going to say turns litmus paper. And I'm going to have you write the word turns because I realized last period we didn't write that part down in it. And when they got to that question, they got a little confused. So turns litmus paper, not what the litmus paper is. turns litmus paper. An acid will turn it red, and a base will turn it blue. Our next thing is our differences in pH. So our acids have a pH less than 7, meaning 0 to 7. And actually, it can go below 0. Our bases have a pH greater than 7. All right, so let's start with acids. So the next thing about an acid that they have is that they react with carbonates. So a base will not. Okay? So acids will react with carbonates. So for example, baking soda. If you've ever done the little volcano experiment where you put some vinegar and then you put baking soda and it goes whoosh, right? That's that neutralization reaction right there. It's also why Miss Fogel, in your guys' little crates around the room, part of the spill kit is not just the kitty litter, but also baking soda to neutralize any acid. But if you pour it onto a base, nothing would happen because it doesn't react. All right, so they react with carbonates. It's sodium hydrogen carbonate. That's what baking soda is. So it's a carbonate. Acids will also react with metals. Okay? And then put an arrow saying they're going to form hydrogen gas. Okay? So they react with metals to form this hydrogen gas. Sorry, that just says gas. I'm realizing you can't read it. All right. Bases, on the other hand, this is their big difference, they feel slippery. So best example of that is think of soap. Okay, so bases will feel slippery. And there's a special indicator that we always use for trying to figure out if something is a base, and it's called phenolphthalein. So, you guys ready to spell it? It's a long word. All right, so just take your time. Make sure you write it down. This is the only place I'm going to make you actually write the whole word. Phenolphthalein. Phthalein will turn pink. For an acid, it will not do anything. It will remain colorless. Okay? So, we use phenolphthalein for something called a titration, and I'm hoping you guys will get to do a small version of that in your little property station thing. Okay? So titration is just a neutralization. All right, cool. Last little bit. This next part is really short. So we're gonna review our strong acids and bases. So go ahead and look at the top right. Strong acids and bases. So our strong acids, we had two categories, binary acids. Okay, for strong, it was I bring clay. You guys remember writing that? I bring clay, not food. Okay, so I bring clay. What that tells you is HBr, HCl, HI. Okay, so HI, HBr, HCl. Any of those are the strong binary acids. Okay, there's only 3. Then we talked about for oxy acids, there was a rule because I felt like it's more difficult to try to memorize a bunch of these formulas and names. So the one rule that we had was you had to count up something. Does anybody remember what that magic number was? 2. It's 2 or more oxygens than hydrogens. So 2 or more oxygens than hydrogens. If it has 2 or more oxygens than hydrogens, then that means that it is a strong acid. Okay? So for example, if we had something like, I'm going to write it right here, HClO3, we have 3 oxygens and 1 hydrogen, right? So 3 minus 1 is 2, so 2 or more oxygens than hydrogens. So you're kind of focused in on counting up with those subscripts. You just want to get 2 or more because it makes it 100% ionized. All right, and then for strong bases, we formed the letter B on our periodic table. So we formed the letter B on the periodic table, starting way up at lithium, and then going down sodium, potassium, rubidium, and cesium across to barium, strontium, and ending at calcium. So this is group 1 and group 2 on your periodic table, right? Any of those attached to an OH were our strong bases. And our general rule with all of these is that if it's not strong, it's weak. Right? That was the general rule. So as long as you know what your strong ones are, if it's not on that little VIP list, then it's going to be a weak acid or base. Okay, so that was a little review of that part. So the last thing that we're going to write, pretty simple, is a neutralization reaction. That your goal of a neutralization reaction is that you're trying to get close to a pH of 7 or exactly 7, right? What is the beverage that we can drink that has a pH of 7? Water, okay? So with that, just so you know, water is H2O. That means it consists of an acid, and it also consists of a base. That's what makes that pH right in the middle. The fact that it has acid and base in it, in the formula, makes it that neutral idea, okay? All right, so when you are looking at a neutralization reaction, it's just going to be a little acid. So this is just your H with an anion plus a base is going to make a salt and water. Okay? So acid plus base makes salt and water. And that's it for that. Okay? So this is a very common question. What are the products of a neutralization reaction? Okay? You'll see that one today. All right. As far as this pH scale, I'm not going to go over calculations because I don't want to overwhelm you with tons of new information. But what you do see is that we do have the words acid and base right here. This is the pH scale. pH means power of hydronium. So pH is talking about kind of the acidity of something, right? Whereas the pOH scale, all that you see is different. It still goes the same number range, right? But now we're changing acid and base where they're located, right? So you kind of see that. The part that you're going to need today is talking about the fact that 14 means strong and 0 means strong on either scale, okay? Your 2 endpoints are strong. Draw an arrow pointing to the right and draw an arrow pointing to the left from that neutral. What this is telling you is this is going in order from weak to strong. So you do have a question that's asking you to rank the different pHs of a base. So you're going to be going from 7 to 14. That's your scale. Then you have one that's going to ask you to rank from weak to strong of your acid. You're going from 7 to 0. So you see that it's not one directional, right? It's about this is the midpoint, this is the weakest point, we move away from that. Okay? When you get to those questions, you'll see what I'm talking about there. I think you'll be fine. The only other thing that will help you as far as the questions go that you're about to see is the fact that soda, which I have said this, but we might have forgotten already, is this. So if I tell you that that's soda water, then is that an acid or a base? That is an acid. There's an H right here, right? So this is an acid. All right. And window cleaner contains NH3. So is that an acid or a base? Window cleaner contains ammonia. So is that an acid or a base? Base. Yep. Okay, and that's all you guys need. So now I will hand out your little paper. You have the rest of the period to work on it, get it done, and yeah.